So we're going to look at some new strategies for solving equations, and these strategies often involve identities, factoring, some fraction work that you know from before. So this is a good example to start with. We have cotangent and we have cos, which is a problem because they're different trig functions. So one of the main strategies is, if you could change everything to the same trig function, that would be wonderful. But unfortunately, can you change cotangent to just cos? No. So then we go and we say, well, I know I can change cotangent to cos theta over sine theta. Maybe this will help. Because you can always change things to either sine of theta or cos of theta. But then this gives me an equation with a fraction. And because it's an equation and not a proof, you can move things from one side to the other. If you wanted to get rid of that fraction, can you see you could multiply everything by sine? And if I multiplied the left side of the equation by sine of theta and the right side of the equation by sine of theta, well, on the left, that would get rid of that fraction. And I would be left with just cos theta equals 2 cos theta sine theta. Once again, I still have two different trig functions. I can change sine squared to 1 minus cos squared, but sine without the squared, you cannot change to cos. Not easily. Okay? So in this question, we're going to get another strategy that comes up, and that other strategy is factoring. We will always make one side equal to 0 when factoring, because then we can use the zero product property. And in this case, both of these terms have a common factor of cos. In your mind, I want you to think what would be left if you take that cos out, because there's some common mistakes here. So think about what would be left. I'm going to take a cos out of both of those terms. What is left? Okay. I'm going to do, if you take a cos out of a cos, does it make sense? You're going to have a minus 1. That's generally not the place where students make a mistake here. The mistake happens here. When you take a cos out of this, taking a cos out is like dividing it out. You're still left with the 2, and you're still left with the sine theta. Okay? Sometimes, and maybe you did this, when you see 2 cos and you think I take 1 cos out, I'm left with 1 cos left, that is wrong. Because taking a cos out is like dividing. The 2 would still be there, the sine would still be there, you've divided out the cos. The reason factoring is important is because now we have multiplication here, and when two things are multiplied and they equal 0, either the first one's equal to 0, or the second one is equal to 0, in which case, if I made it equal to 0 and solved, sine of theta would be 1/2. These values are on your pie plate. When is cos 0? Pi over 2 and 3 pi over 2. When is sine equal to 1/2? Quadrant 1, pi over 6 family, and quadrant 2, 5 pi over 6. Now, I'm in the habit of solving between 0 and 2 pi. I should go back up and see, what did they say? Oh, I made this question. It's between 0 and 2 pi. I knew I'd make myself happy by not changing the domain. So these are our answers. So this question used the strategy of changing to sine and cosine. They gave you a fraction to get rid of your fraction. We still didn't have a single trig function, so then we looked, could factoring break them up? Because you see how factoring separated them. So I had cos all by itself here, sine all by itself there, then it's solvable. All right, next little bit of notes. Still, if you have room on 666, but if not, you can write this on 667. What's going to happen now is you're going to get solved equations with 2x in them. And sometimes they're going to be multi-revolution questions like we did in the past. And sometimes they're going to be double angle identity questions, which are new formulas that we just learned the other day. So the question is, how do you know which strategy to use? The multi-revolution or the double angle identity? And here's a basic breakdown of being able to tell which one to use. So you see that it only has the trig function with the double angle identity, then use multi-revolution strategy. But if you have the double angle and another trig function, then you should probably use one of your double angle formulas. So we'll look at solving both of these. We'll review multi-revolution idea that we learned before. And we'll look at how to use our formulas. All right, so let's look at the multi-revolution first. You have this question, solve between 0 and 2 pi, cos 2x minus root 3 over 2 equals 0. So you could get the cos 2x by itself. And a reminder, in a multi-revolution question, we first rewrite the domain for 2x. So if x was between 0 and 2 pi, 2x's would be between 0 and 4 pi. Twice around your circle. Is cos ever root 3 over 2? Yes, that is our pi over 6 family, positive in quadrant 1 and quadrant 4. That's the first time around. Then the second time around, what's coterminal with pi over 6? Well, you would have to add 2 pi to find out what's coterminal with it the second time around. And of course, 2 pi is 12 pi over 6. If I add 12 to 1, I'm going to get 13 pi over 6. If I add 12 pi over 6 to 11 pi over 6, I'm going to get 23 pi over 6. And then you can solve for x by dividing everything by 2 or multiplying by a half, which will change all the bottoms to 12. And all of our final answers here are between 0 and 2 pi. But if you have a double angle, so now I have sine 2x, but I have another trig function, then the multi-revolution strategy will not work. And so in the second example, we will look at our formula sheet and see that I can change sine 2x to 2 sine x cos x. Now at least my angles are dealing with the same angles. Because before, if I put brackets here around the angles, right? My one function has a 2x as an angle, the other function has an x. So we want to solve it so that we're dealing with just an x for an angle. Okay, I'm looking at this. Can I change it all to sine? No, because it's not cos squared. If it was cos squared, I could change it to 1 minus sine squared. Cos, I cannot change to 1 minus sine. Like, you will be tempted. You will want to do that, but no, not allowed. So then we look, can we use a factoring strategy? And if I move everything to one side and make the other side equal to 0, do these have a common factor? They do. I can pull out the sine x, leaving with 2 cos x minus 1. So sine x could equal 0. And cos x could equal positive 1/2. This is on your pi plate. 0, pi, and 2 pi. And cos x equals 1/2. Pi over 3 quadrant 1. 5 pi over 3 quadrant 4. So it's noticing the difference between using a double angle identity and using multi-revolution. Sometimes the multi-revolution ones, there are ways that you can use double angle formulas and it still works as well. So there's possibilities there. But this is a way to separate which ones you can use. So let's turn to example 4. We have a 1/2 sine 2x minus cos squared x equals 0. So I see right here, I'm going to underline it, I have a double angle identity. Should I use multi-revolution? Not in this case, because I have another function. So the first thing I'm going to do is I'm going to go to my formula sheet and see what can I change that double angle to. And my formula sheet says that sine 2x is 2 sine x cos x. In fact, it's really nice. Those 2's will cancel out. And I'm left with sine x cos x minus cos squared x equals 0. So I look at this and I go, I could change the cos squared x to 1 minus sine squared x, but I would still have a cos x here. I can't change the sine x because it's not squared. So I feel like I can't get everything to either sine or everything to either cos at this moment. If you think you might be able to, try. Okay? It's actually a good mathematical strategy to try techniques that don't work. You get better at math by exploring something even if it doesn't work. It's not high on the feel good scale, because when you try something that doesn't work, you get sort of frustrated, but you do learn a lot of math. So sometimes in these questions, and especially in proofs, you have to try stuff. And you go until you're like convinced like this is not working. Then you have to go right back to the beginning and try again. Maybe try something different. For proofs, that's the number one strategy to get better, is you have to just try something and see where it goes. Then try something else and see if you can eventually get the left side to equal the right. So here, I could change to sine squared. I did it in my head. It doesn't get me anywhere. So then I'm going to say, well, I could try factoring. I'm not really happy with the factoring. Like this part of the factoring I like, because this I can for sure solve something. Oh, I can get some marks. I know that cos x has to equal 0, and that happens at pi over 2 and 3 pi over 2. This part I'm not really happy with right now because it still has sine and cos. But there's a couple ways you can do this. Can you see that if this was equal to 0, if you moved, that they would have to be equal to each other to equal 0? And we've done this question, I think, a couple of days ago. You remember how we solved this one? You could either look at your pi plate. Is you ever have the x coordinate and the y coordinate the same? Yeah, root 2 over 2 and root 2 over 2. When does that happen? Well, it happens at pi over 4. Does it happen anywhere else where the x coordinate and the y coordinate are the same? In quadrant 3, they're both negative root 2 over 2 at 5 pi over 4. Or you could take that equation that you have right now and divide both sides by cos. And you would get tan x equals 1, which also is on your pi plate, and give you pi over 4 and 5 pi over 4. So now in your textbook, you can circle 12, 13, 14, and 15. And on the back side of your proof sheet, that one where you had all the proofs, on the back side was a bunch of solving questions. I would like you to take out a highlighter and highlight the following questions. The reason I say don't say circle is some questions are already circled, but those aren't the ones I'm assigning. I'm going to get you to do 8, 9, 11, 12, 14, 15, 21, 27, 29, and 31.